Okay. Now, the interesting thing is right now we're going to do area between the curves. So let's say you had your axes here, and you had a parabola like this, and then a line like that. And those two curves, get out our fancy crayons, feel like red today. Oh, this is bad coloring. All right. There we go. Nicely colored.
Oh, it all shifted down. Yeah, it all shifted down a bit. Went across the line.
So we're going to find the area between these. Now, it's going to somewhat work, well, it is working off of an idea that we've already learned. We already figured out how to find the area under a curve to the x-axis. So can you imagine, let's just take this section right here, okay? Can you see that if I found the area under the blue curve, and then I subtracted the area under the green curve, I would be left with the area between them. Does that make sense?
Yeah.
So if I find the area between the blue curve and the x-axis, and then I subtract the area from the green curve to the x-axis, I would be, that would just do, I'm just doing this section here. Okay? What about what happens when things go underneath the axis? Does it cause a problem?
Did you just like not find the area above the x-axis, so like in the negative also above the x-axis?
Like this part here, I'm just talking about this little black section.
You said the area under the curve, the blue one, wouldn't that be all positive?
Oh, like keep going down?
No, like
This section that we haven't talked about yet, you want to talk about?
but like the one above the x-axis, wouldn't you find that?
Like this part here.
He'll do it later.
Okay? Let's talk about this part here right now. If I find the area under the curve of the blue one, that would give me this part. And if I found the area between the green curve and the x-axis, that would give me this section. But what would happen with that section because it's below? It would be negative. And so in the first part, I talked about taking what's under the blue curve and subtracting the yellow to get the red. I can do that same process in this part. If I take the blue part and subtract this, because that's negative, when I subtract a negative, it adds it. That would give me all of this red area by subtracting again. And in this last little part, the same thing would be true. And so what's really neat about when you're finding the area between two curves, we're going to find out that all we have to do to find the area between the two curves is figure out which function is above the other function. In our case, can you see that the green function is the top bound and the green function was the bottom bound for the area that was enclosed between them? And if you subtract the two functions from the 2 points where they intersect and do the integral between those 2 points, you will calculate the area between those two curves. And it does not matter if part of it's above the axis and part of it's below, or if it's all below, or if it's all above. Which now we can find some really interesting looking areas. So one of the things that we're going to have to figure out is which function is above and which function is below. So you're going to want to sketch these quickly off to the side. So here I have this one which I'm underlining in blue, and I'm going to quickly underline this one in green. Without any axes, what do I know about the blue graph? It's a parabola that opens up. There we go. What do I know about the green graph? It's a parabola that opens down. Now, it could be that they never intersect, but if they do intersect, I will create an area in between.
Did Jets win yesterday, or did they lose?
So what we're going to have to find then is where they intersect. If I want to set up this integral of the area under the green curve minus the area under the blue curve, I need to find out where they intersect first.
We would just put you array you
Make them equal to each other.
or you can minus one from the other.
Or you could subtract one from the other. That would work as well. If you make them equal to each other, what would we get? We would get x squared plus 2x plus 2 equals negative x squared plus 2x plus 10. It's quadratic, so move everything over to the other side. And we find our values where the two graphs intersect. So then to calculate the area between those two curves, we're going to be looking for the integral between negative 2 and 2 of the green graph minus the blue graph. So our green function minus our blue function. Now, one of the things that sometimes happens in these questions is you get overexcited to find the integral, and you start integrating all 6 of those things separately. You can do that, but why not simplify things? If I simplify things, I'm going to get negative 2x squared plus 2x minus 2x. That goes away. 10 minus 2 plus 8 dx. Yes?
Could you explain why like the green area from -2 to subtract the blue area from -2 to like
Is that area in between?
like if you draw a graph of
Like what I was doing at the beginning of class?
like an x and y axis. Yeah, you draw an x and y axis like.
Okay. Where do you want your x, like where they actually are, or
Well, like yeah, I guess. Just estimate. I just want to visualize it.
you want to visualize it? Okay. So this is going to be what happens here. Well, I'm just going to. Is that true? I'm not. Is it going to be further up? It's probably going to be further up, right? There's probably. It really doesn't matter. You can put it.
No, it's +2.
Are they both above the?
Yeah.
It's like that. Okay. This, if it's like this, it's really easy to visualize what's happening. Okay? So when I am finding from -2 to 2, when I do the integral of the green part, what is that going to find? That's going to find the whole area of the green all the way down to there. When I find the integral of the blue part, that'll find this area that's white right now. And if I find the whole thing, subtract the white thing, I'll get that football-shaped brown crayoned area that's left.
So is the brown crayon.
And it doesn't matter. This holds true whether the axes are up here, over here. Doesn't matter where they are. That's going to hold true no matter what.
How do you know which one to subtract from?
You always have the top function subtract the bottom function. Again, that's really easy to see if I move the axes below here.
Top function, you mean like,
The green one is the y values are higher.
oh, okay.
Okay? So I'll call that the top, the upper limits of the shape, the upper border minus the lower border.
If you do it the wrong way, you get a negative, so you just.
Yeah, if you do it the wrong way, you get a negative answer. Then you go back and just put absolute value bars all the way through so you don't have to erase it and start your question again.
Actually, do that?
Sure,
Yeah, we'll have to look.
because you'll realize you made your mistake. But now that we've simplified it, the integral becomes add 1 to the exponent and divide. Plug in 2. Plug in negative 2. And you would get 32 minus 32 thirds.
And that'll be 32/3 for the first bracket.
What's that? I put my like terms together first. So I went 16 plus 16 to get 32. And I went minus 16 thirds minus 16 to get 32 over 3. And then simplified it from there. So what we just did is we just calculated an area that has a very weird shape. No straight edges anywhere. And just by knowing that the area under the curve to the x-axis is the definite integral, and subtracting the other area, we can do that. Just quite powerful. Here's one for you to try.
So the second equation,
I like to color code.
what if we don't have colors?
Pencil and pen. I like to color code them so I can realize which function when I draw a sketch. Right? One of them is a parabola opening up. The other one is a line.
No, just by looking at the y values, that the second one is the big one that goes.
So when we shade the area, we can tell that the green function is the function that's on top. If you want to check to see how you are doing, first of all, you got to find out where they intersect. Were you able to get 4 and negative 1? Okay. Again, this was the line, subtract the parabola. So simplifying that, you would have got negative x squared plus 3x plus 4, integrating, plugging things in, and we get 125 over 6. How did I get 44? This is 24, and that's 40, and then plus another 4. So I find for mental math stuff, I like to simplify like fractions together first. Work. First of all, the solution, did you get negative 2 and 2?
Yes.
Good. So you set it up with the line, subtract the parabola. Simplified things, get negative x squared plus 4. Integrated. Substituted in. And get 32 over 3. Were you good up to here? Do you need to scroll up a bit? Okay, here's our last example. We have a cubic graph and a parabola. And we need to find out where they intersect. So if we start off by equating the two, x cubed plus 2x squared equal to x squared plus 2x, set that equal to 0. X cubed plus x squared minus 2x equals 0. First of all, notice that you have a common factor. You can factor that out. And then you can factor it completely. It's going to be plus 2 minus 1. So we have 3 places that these graphs are going to intersect. They're going to intersect at x equals 0, x equals negative 2, and x equals 1. Now I'm going to color code my graphs. I'm going to go f of x in blue, g of x in green. And I'm going to draw a little bit more accurate graph than we have in the past in this situation. So starting off with f of x equals x cubed plus 2x squared, can you see that you could factor out an x squared out of that and get x squared x plus 2? So that would tell us that we know that we have an x-intercept at 0 and an x-intercept at negative 2. And it bounces at 0. So getting the general shape of my f of x graph looks like this. My green graph, that too can be factored. It can factor to be x times x plus 2. So we have the same x-intercepts. Okay. And we know that the two graphs intersect at negative 2, which we can already see from x-intercept, 0, which we can already see, but also here at positive 1. So if I'm shading the area that's bounded by these two regions, there's actually two different parts that get shaded. This part, which is easy to see, which this will be hard to remember. We're going to refer to this as the purple shaded part. Okay? And then if I keep crayoning it, you'll see it better and better and better. And this section, which we will refer to as the orange colored part. We've got an orange section and a purple section. What makes this question a little bit different is they swap. In the purple colored section, your top part is the blue function. But in the orange section, which is so lovely, deeply colored in orange, you can no longer tell, but the green one is the function that is the top function. So we have to set up two separate integrals for this and add them together.
You sketch like the x squared graph, like the sketch out a little mall. You can easily just make the blue one go over it just by the sketch, because they're so close together.
They're so close together that you could accidentally assume that the, well, what you have to do in as far as figuring that out, that's a good point, right? What happens if I drew it and I just thought mine, an x cubed graph increases much faster than an x squared graph. So if the x cubed graph were on top and a parabola is underneath, There's no way that parabola can ever catch up to that x cubed graph. So the fact that they do intersect again, you have to use a little bit of mathematical, I'm going to call it mathematical knowledge. I was going to say mathematical common sense, but this is complicated common sense. So I think as soon as you call something complicated common sense, that doesn't necessarily mean it falls into common sense anymore.
It's complicated.
Complicated common sense. The fact that you know that an x cubed graph increases at a faster rate than an x squared graph. Okay?
Increasing it faster, how is the x squared graph at any point ever equal to other than zero? Like after that point.
After, yeah, well, at this point it's above, but eventually it comes back and swoops up again.
All right.
Okay?
Sure.
So, but that can be a complication that you might run into. If you're running into that complication, you can always plug in values near to the intersection point to find out, okay, which one is higher at this point. For example, I know that one of the two graphs has to be bigger between 0 and 1. If I plug a half into both of those equations, which one produces a larger value? And plugging a half into the green function will produce a larger value for y than plugging a half into the other one.
So if they're intersecting at 1, you could just put 1 in and see which one is
So
higher.
1 would be
Or
0.
what is it intersecting?
No, 1 will give you the same value for both.
Right below.
1 would give you the same value because that's where they equal. So that's why I chose a half somewhere in between there. So we have to figure out two integrals and add them together. We have to figure out an integral that represents the purple area. And we have to have an integral that represents the orange area. That one is nice. The first one was pretty good, but the second one is artwork, forever to be shown on YouTube.
That's pretty good.
Okay, and since yeah, since those integrals are nice, we have to finish our work using nice pens. So we'll go here. This first one goes from -2 to 0. And in that section, right, our blue function, which was the cubic one, is on top. So we would have x cubed plus 2x squared minus, and the other one was just x squared plus 2x. Dx. And in the second one, it's the parabola first minus the cubic. And that one runs from 0 to 1.
You can't do that on ours. Oh, come on.
So simplifying these, we're going to have x cubed plus x squared minus 2x dx. And here we're going to have negative x cubed minus x squared plus 2x dx. And this one goes. Gets pretty long, right?
We find space on our paper for it.
I should have maybe had some values a little bit smaller, but some of them are quite easy. Like I didn't need to make these first set of brackets so big, right? Plug in 0. Life is pretty good. Plug in -2. 16 over 4 is 4. Minus 8/3 minus 4. Okay? Plug in 1, -1/4 minus 1/3 plus 1 minus 0 plus 0 plus 0. And you can see that those will simplify, right? And so what do we get? We get 8/3. You want to add that? Well, it'll be positive 7/3, right? This is positive 8/3 plus a -1/3. 7/3 minus 1/4 plus 1. So this is 21 over 12. This is 3/4, which is 9 over 12. Hmm?
30 over 12 simplified to 21. Which you can simplify to 2.5.
And you can divide them both by 6. Is that right?
Yeah, 2.5.
2.5? 21 over 12. This is 3/4, which is 9 over 12.
But 7 over 3 is 28.
Oh, 28, yeah. I did 7 times. There we go. 37 over 12. There we go.
Okay, I wasn't going crazy.
You weren't going crazy. Nice. Now let's look at how our calculator can get us this value and what it looks like on our calculator. So how can we use the values on our calculator? We're going to type this same thing, one equation into y1 and the other one into y2. So our first equation was x cubed plus 2x squared, is that right?
Oh, yeah.
Something like that's not quite good enough.
X cubed
And then
plus 3x squared is
x squared plus 2x.
squared.
And I'm going to go zoom 6 to see a standard window to see if our graphs match up. There's the one. There's the other one. Okay? We want to get 37 over 12 in the end. That's our hope. Okay. Now, with the integral button finds the area under a curve. It doesn't find the area between the two curves. Okay? What I can do in here, though, is in y3, I can take, remember that this is, for the first little section, from 0 to 2, or from -2 to 2, we would want to do the blue graph minus the red graph. So something I can do in here is I can go y1 minus y2. Variables, y variables, functions, and instead of retyping them all, I can do y1 minus y2.
Variables, which is right underneath you.
Oh, here. You can grab this one if you'd like.
Oh, yeah.
Okay?
That's actually a nice feature.
It is a nice picture. So now if I put that in, I get this new graph in black.
Oh, yeah.
And now with that black function, I can go second, calculate number 7. And you got to be careful here because notice that it's on y1. I can alternate between which function I want to use, okay, by just going up and down. I want to find the area from -2 to 0 on the black graph because the black graph represented one subtracting the other. So I'm going to go from -2 to 0 on the black graph, and it shaded that section.
How do you do that?
2.666667.
How do I select the one that's on the black line? That's the calculation.
I'm going to take that answer. The neat thing is your calculator has whatever answer you just figured out, and I'm going to store it as A because it's the first thing I figured out. That way it keeps all the decimal places. I can go back to the graph. Now, I have a lot of things on here as a graph. Sometimes I find personally that having so many graphs on there at once gets it confusing. So another thing you can do on the y equals is you can go to the equal sign and push enter and see how it unhighlights the equal sign. And now just the black graph is going to show up. I didn't have to erase the other graphs to have them not show up, but it makes it a little bit simpler when trying to figure things out.
If you erase the other ones, it won't work.
Yeah, if you erase them, then you sort of like, well, now there's nothing in y2 to minus y1. And so now I can calculate that integral again, number 7, from -2 to 0, and it really shows that well. The shady thing shades automatically when you go to the calculate and you do the number 7, which is the integral. Okay? Now, we could go to y4 and do y2 minus y1. What's that going to do to that black graph? It's going to just flip it. Or I could just go second, calculate the integral from 1 to 0. Oh, I did the wrong order. Clear. Oh, this will actually do exactly what I want, but not what I wanted to show you. Yeah, so I went the wrong direction, made it positive anyways. But in 7, what is our lower limit? Our lower limit is 0. What is our upper limit? It's 1. Finding that area. Notice that my answer came up as negative because that area is below the x-axis. Okay? But now, if I wanted to figure out what the actual area would have been, it would be the flip of that, which would make it positive. So now I can go, I know that my last answer was that -0.41x. I'm going to go and just make my last answer negative. I'm going to add a to that. Those are those two areas together. Change it back to a fraction and hope we get 37/12. Amazing. There was too much calculator math, I know.
I'm so lost in other stuff.
Quick question.
Yes.
The third equation that you get from the other two equations, I noticed it has two areas.